spoke about a complicated theorem, and I spoke about treating games as graphs. So today we're going to try to come to terms with that. We're going to try to basically play one of these games and see how far we can get. So you've each got a piece of paper in front of you, circles on it, connected by arrows in some way or other. Something like this. Right? It's your own different game. One of you now in the pen, call yourself Alice, and the other one Bob. You've each put a smartie. You've each put a smartie on some starting square. And the game goes like this. Alice moves the smartie to some square connected to this one, or some circle connected to this one by an arrow. So Alice could make this move or this move. Bob then moves the smartie from the next stage to one of its neighbors, and so on and so forth. Right. Until nobody can move. The last person to make a valid move gets to eat the smartie. Alright. So that's basically your Alice or Bob, right? So, okay, let's all play this game a couple of times to get an idea about how it works, about how it's dependent on the graph structure. I've given you each 3 smarties. They're good for 3 games. Please start as Alice. Whoever starts as Alice should be Bob on the next turn. Let's just call this a spread-friendly game. Alright, so everybody's playing. I suppose for the camera's sake we should play one game in front of the camera. Okay. Okay, I'll be happy. Now you get to move. Alright, so that's the last move. Bob wants to go get eaten. Alright. Play another game. So now, and what did I do last time? I did this. Bob moved to the game. And last game for us. So this time, this game, I think Alice is So Bob wins all 3. Okay, so I'm assuming you've all played at least one game. By show of hands, Alice, did you win?
Yeah.
Alice, there. I was Alice. I lost 3 times. Is there a Bob who won? There's a couple of Bobs there, so quite a couple. Alright, so there were 2 different game boards circulating. I'm going to mix things up a little bit, but before I do, we're going to try and analyze this idea of a game and see what we can do with it. Now, we already spoke a little bit about the analysis of these games previously, but now that we've all played one for a little bit, let's do it. So I'm going to do the one on the board, and you guys are going to have to do the same analysis to your game in front of you. The first thing I'm going to do is I'm going to label each of the vertices. So I'm going to call this vertex 1, vertex 2, vertex 3. In fact, I'm going to write them inside, easier. I gave you a nice big inside. And for my game, I want there to be a unique version position. Alright. So, the game I've got on the board has got 6 vertices. So I would write its vertex set as 1 to 6. This game also has functions that map each vertex to a set of other vertices. So F, which maps G to a subset of R, right? To essentially the power set of B, is given by F of 1, is the neighbors of 1 for me is 2 and 3. F of 2, that's the neighbors of 2 for me is 3, 4, and 5. F of 3, that's the neighbors of 3, in this case just 5. F of 4, that's 5. F of 5, that's 6, 7, and 8. F of 6 is empty. F of 7 is 6. And F of 8 is 7. Okay, so I've completely described the game on the board. It's your task to look at the game in front of you and describe it in the same fashion. So, tell me, label the vertices, give them all labels, right? Try to label them left to right if you can, but it doesn't matter if you don't label them uniquely. And then, for your labeling, define the function f that maps to each vertex its neighbors, right? The things that come out of it, right? Once you've done that, it's going to be a question as to what is the optimal strategy, and in order to compute the optimal strategy for this game, we are going to define the frag-ready function on the game. Okay, but just let me know by show of hands if you have finished finding your game, and when that happens, we will carry on. I suppose we should do this one. 13 vertices, and for us, so here's the game.
Okay.
I put it from end to beginning, so I labeled them in a very strange way.
Okay.
Because this should be 1, but anyway, it doesn't matter. Now we say f of 13 is 9 and 12. F of 12 is 9, 8, 11. F of 11 is 8, 7, and 10. F of 10 is 7. F of 7 is 5. F of 8 is 7, 5, 6. F of 9 is 8, 6. F of 5 is 3 and 4. F of 6 is 4. F of 4 is 2. F of 3 is 1. And F of 2 is 4.
Yeah.
Alright, so has everybody discovered? Yes. Oh, there are 8. Very well spotted. Right, good thing someone was awake. Right, we looked up here. So the one game that I've looked at here has got 13 vertices, and some of you have got a game with 12 vertices. Okay, so they both have 13 vertices. So the games you've got have got 13 vertices, but you do have 2 different games. Okay.
That's mine. No, I mean, it's good, like, it's actually your
Show of hands, how many people have done this now? Up to the 13th vertex. One back, front, just one down. Okay, I think we'll move on. So please just concentrate on the board and you can go back to working in a second. I want you to look at this graph over here. Where is the last position? There may be more than one in some graphs, but in this case, there is one place in which if you find yourself there, you lose. It's number 6. Right. I'm going to call the Sprague-Grundy number of 6 0. Okay. I'm going to assign a 0 to 6. Now before I even tell you what this number is, I'm just going to compute it for this graph. 7's only neighbor is 6. Okay, 6 already has a 0, so 7 has to have a 1. Alright? 8's only neighbor is 7. 7 has a 1, but none of 8's neighbors have a 0, so 8 is going to give a 0. 5 neighbors. Okay, so the way this number works is I look at all the neighbors of the vertex that I'm at. And I say, what are their numbers? And then I ask, what's the smallest number not there? Okay, so for 6, there are no neighbors. The smallest number I can write down is 0. For 7, there's one neighbor at 6 that already has a 0. The smallest next number is 1. For 8, its neighbor is 7, it has a 1, but nothing has a 0. So 8 can put down a 0 because none of its neighbors have a 0. 5 has a 0, a 1, and a 0. Therefore 5 has to put down the smallest number that is not 0 and that is not 1. So for 5, the number is going to be 2. For 3, its only neighbor is 5, right? We can check by looking here. Its only neighbor is 5, so what number did we assign to 5? We assigned it 2. That means 0 is free. So 5 can call itself, 3 can call itself 0. For 4, its only neighbor again is 5. Yes?
We just start with the lowest one.
Start with the lowest
one. Yes, because we can either pick 0 or 1, right?
For which one? For 3?
Yeah.
Yes, so we pick 0 because it's smallest. If there was a 0 that was its neighbor, if for example, if I'd drawn this line, then I would have to pick 1. Right. Okay.
Because you can only pick another slope.
In fact, let's draw that line and make this funner. Alright. Now, 4 has only one neighbor, and that is to 5. So 4 can put 0. If I've drawn that line, by the way, then 3 also has to have a 6 in it. Okay. 2 has got 3 neighbors. The neighbors of 2 are 4, 5, and 3, and they have 0, 1, and 2. So the number for 2 has to be 3. And finally, 1 has got 2 neighbors, and there are 1 and a 3, so 1 is 0. Okay, so that is the Sprague-Grundy numbering of this graph. And it is intimately tied up with winning and losing. It can even help you with multiplayer games. But let's just look at how it's tied up with winning and losing. Right, the Sprague-Grundy number is 0 in a configuration where if you have to play, you will lose. Okay? Now, anything that can play into a 0 has a Sprague-Grundy number that is non-zero. Right? And anything with a Sprague-Grundy number that is non-zero has dropped a 0 neighbor somewhere. Okay, so if I start at 3, I can play to 0 by definition of being at 3. I can play to 0, 1, or 2 in fact, because that's the definition of 3. My neighbors have got a 0, a 1, or a 2. The important property that we care about is whenever you're at a 0, whenever you're at a non-zero number, you can always play to a 0 number. Right? But whenever you're at a 0 number, you can never play to a non-zero number, by definition. So, any position with a non-zero number is a winning position in a 2-player game. Okay, let's have a look. If I'm at 3, my winning strategy will be to play to 0. Now if I'm at 4, I'm at a 0, I'll do what I can and play to 5. I'm at now 5, I'm going to play to 0. That's my winning strategy. So I play to 8. The guy at 8, there's no choice, play somewhere, play to 7. And then I play to 0. Right, you see, so the strategy to win the game is to play to the 0. Okay, I want you all to compute the Sprague-Grundy function for your games that you've got in front of you. Remember, the Sprague-Grundy is a function because it maps vertices to numbers. So for us, for this one, G of 1 is 0, G of 3 1, G of 4 is 0, 5,
So we can start with the vertex we label 1,
Yeah.
and we can say this one has a 0. The only thing going out of this 2 is that one. So the Sprague-Grundy function here is 1. This 3 is the same story. Its only neighbor is this, which is a 0. So its Sprague-Grundy function is 1. This 4 has got only that as a neighbor. Its Sprague-Grundy function is 1. So this one has to be 0. This 6 has got a neighbor of 4 only, it's got a 0, it's 1. This 5 has got neighbors out of that 4 and the 3, that's a 0 and a 1. So the 5 is Sprague-Grundy 2. 9 now goes, I can't do 9, I have to do 7. Because 9 goes to 8 and I don't know the number for 8 yet. Okay, so 7 goes only to 5, it's got a 2, so 7's got a 0. 8 then I can now do. 8 goes here and here, that's 0 and 2, so I can put in a 1. 9 goes here and here, that's 1 and 1, so 9 can quite have a 0. Then 13 goes here and here, no, sorry, I have to do 10, because that only goes here, so that's got a value 1. Then there's 11, which has 0 and 1 as equivalent, so that must be 2. Then there's 12, which has got 0 there and 1 there and 2 there, so 12 has to be 3. And finally 13 goes 0 and 3, so this can be. So your winning strategy, if you were here, you'd play there, and then from here you could play wherever, maybe here, and then from here you'd play there, and then from here you'd play wherever, maybe here, and then from here you'd play there, and then from here you'd play to here, and then you would. So you always play towards 0.
So you can say the way you have to follow to color.
Yes, there is. You must always color it in such a way as to start with the one that has no label. Otherwise, if I try to start here before I label them, right. So you start with the guy who has no name. You always give him 0. Then you look at things that come into that. Like the concept there. Both of these are fine because neither of them have got neither of these have got other names. So I can immediately do these. But now, for example, that I've done this, I can't go backwards to this one yet until I've done this. See? So I don't go backwards here. I say, well, what else could I do? Go backwards here and fill this one. Now I can do that. So you always have to fulfill all the requirements before you do.
It doesn't matter what you want. I have enough time. So whenever you are so whenever you're running that business,
Huh?
We had a mistake.
Am I?
That's a 0. This one has got a 1 for a neighbor. So I can't choose 1 because of this neighbor. So 0 here, 1 here, 2 here. And that's a 3, then everything else follows. This one obviously can still be a 0. This one is a 1. This one is a 2. And this
And you can all win now if you play from a non-zero position by just playing your opponent into the 0. Right? So if you play this game now, you will eat the Smarty. But I am going to complicate things a little. I'll give you more Smarties though, as a compensation for complicating your life. I am going to add another board. And so you are going to play 2 players. You guys don't eat, so I'm not giving you 2. 1 over there, and 1 over there. Okay? So you have 2 boards. I'll explain to you as I come past. You have 2 boards. On every step, you're allowed to make 1 move. Only 1 move on 1 board. So I can move there, and then my opponent can move there, and then I can move there, and so on and so forth. Right, so you have 2 boards. On every step you make 1 move, and this is the game you're going to play now. I'm not going to tell you who's going to win. You guys. No, this is Okay, let's wrap this up. The first thing we did was we assigned to every game a function g that maps z to its power set. I mean, no, not to its power set, to the natural. Right? This was our Spragg-Grundy function. We've all assigned it to a couple of different games. Basically, it was just in such a way that g at any vertex v is the minimum number n in the naturals such that n is not an element. No, not an element. It's not equal to g of w for all w in f of v. Right? So that's the formal way to write what we all know what to do. Because we all know how to compute these things. We just pick the smallest number in the natural numbers that is not already assigned to the neighbors. So it's a recursive definition of g in terms of g. So we know how to do that. There's a consistent way to do that. We start at a vertex that has no neighbors, we give it 0, and we kind of filter back, which is what we've been doing. Okay, so that's how we assign a Spragg-Grundy function. The next thing I asked you to do is to, so then there's a result. The winning strategy, every vertex with g of v non-zero is a winning position. The winning strategy is just to move to a vertex with g of v equals 0 at all steps. Okay, so some of you have done this for some graphs, others for other graphs. Some of you have done it for the 21 game, but you've all computed Spragg-Grundy functions and figured out winning strategies. Right, the winning strategy is always to move to a vertex with gv equals 0. Okay, so this much is true, and we could prove this winning strategy exactly how we proved that our winning strategy for nim is a winning strategy. Exactly the same way. We just say, for every vertex that has g of v equals to 0, it's impossible to keep it. For every vertex that does not have g of v equals to 0, it's possible to move to one that does, by definition of the Spragg-Grundy function. Okay, and the final